Hello everyone, I am Angelo D. Alagos and I will be explaining or reporting our report in homogeneous linear differential equation. Uh, I will tell you or I will explain to you the meaning of homogeneous linear differential equation. A homogeneous differential equation is a type of ordinary differential equation where all the terms are of the same degree in the dependent variable and its derivatives. In other words, it's an equation where every term can be expressed as a function of the dependent variable and its derivatives. Now, we proceed to our process. A homogeneous linear differential equation is a specific type of ordinary differential equation that can be expressed in the form of PO times d raised to n times y over dx raised to n plus P1 d times d n minus 1 y over dx raised to n minus 1 and so on until Pn minus 1 times dy over dx plus Pny equals 0. Where y is the dependent variable, x is the independent variable, denotes the key th derivative of y with respect to x, and P1x plus P2x, so on, are functions of x. Auxiliary equation. To solve a homogeneous linear differential equation, an auxiliary equation, also known as the characteristic equation, is formed using the coefficient of the derivatives for a second order differential equation where n is equal to 2. The auxiliary equation is derived by assuming y is equals to e mx. It can be written in the form of y is equals to e mx. F of d times y is equals to 0 where fd is a differential operator. Since our y is equals to emx, you can use or it can also be written in this form. And f with respect to d is converted into an m is considered auxiliary form. So if m is a root, in finding the roots, the root of the auxiliary equation, denoted as r1 and r2, or r in the case of repeated roots, determine the form of the general solution. Roots can be found using the quadratic formula r is equals to negative p1x plus positive negative square root of p1x raised to squared minus 4p2 times x over 2. The nature of the roots r1 and r2 categorize the equation into different cases. Distinct real roots. Case 1. Roots are distinct real numbers r1 and r2. General solution is y is equals to c1e raised to r1x plus c2e raised to r1x is equals to y equals to c1e r1x, and so on. Assume that its root can be m1, m2, and m3. Then you can have this general formula, which is y is equals to c1 e raised to m1x plus c2e raised to m2x plus c3e m raised to m3x plus so on until you go to c n e raised to mnx. Once the roots are determined, the general solution for the homogeneous linear DE is constructed according to their specific case, and it involves constants. Examples of arbitrary constants are C1, C2, C3, and so on. So we have our practice problem here, which is d cubed y over dx cubed minus 4 d squared y over dx squared plus dy dx plus 6y equals 0. So we start with converting this differential form into our fe times y. So we've converted our dependent variable, which is this equation, into this form. Now we'll get our auxiliary equation where we let d equals to m for y is equals to e mx. Now we're going to convert it to differential form, which is d cubed minus 4d plus d squared plus d plus 6 equals y 0. Now we'll get our auxiliary form or auxiliary equation where we let d is equals to m. We'll start with m cubed minus 4m squared plus d, or which call m converted to m, plus 6 equals to 0. Now we are going to find the root of the auxiliary equation. The root is when we substitute that of the value of the root in this equation, the auxiliary equation must be equals to 0. So it is given here in our equation here. So our m here is our q and 6 is our p. All possible roots are given by the equation of p over q, meaning that all multiples of 6 and all the multiples of a coefficient of 1m cube is the possible root of this polynomial equation. So our PQ is equals to positive negative 1, positive negative 2, positive negative 3, or positive negative 6 over Q, which is our Q is 1, so positive negative 1. Now, we're taking a guess here, but for me, I guess that the positive 3 over 1, by trying trial and error method, we are gonna get we're performing our synthetic division using 3, then copy all of the coefficient of this equation or these terms. So 1, 4, 1, and 6. Now that we have copied it, in our synthetic division, always copy 1 and under. Then we'll start our synthetic division. Then, this should be negative 4. So 1 times 3 is equals to positive 3. Then you have to add both, so you'll get an answer of negative 1. Then repeat it again, negative 1 times 3. So you'll get negative 3. And again, add both terms and you'll get negative 2. Now you have negative 2, repeat and multiply it again by 3. So negative 2 times 3 is equals to negative 6, equals to 0. Therefore, since it's 0, one of our roots is, or root m1 is equals to 3. Because when we divide 3 into our equation here, we will get 0 when we get in our last term. So this is our new coefficients for our for finding another root. So when we recall in our synthetic division, the first term is always a coefficient which is considered a -1 in our degree. So let's start with our 1m squared minus m minus 2 is equals to 0. Now, our equation is simply m squared minus m minus 2 equals 0. Then if we factor out this equation, we will have m minus 2 times m plus 1 is equals to 0. So our second root is equals to 2. And our third root is equals to 1. Or I rather negative 1. Now, once the roots are already given or determined, we will put it in our general solution, which is y is equals to c1e m1x plus c2e m2x and so on. So our final answer will be yc1, which is c1e raised to m1, which is 3x plus c2e raised to 2x plus c3e raised to negative 1x. So this will be our final answer in our number 1. Now we proceed to our number 2 problem. This equation is already written in differential operator form. Then we convert it into our auxiliary form, which is m squared plus 2m minus 3 equals 0. Now that we have our auxiliary form, we need to find our roots in this equation. So we can factor it with m plus 3 times m minus 1 equals to 0. When you FOIL method this equation, you'll get an answer of this. Since this is a second degree problem, we have two roots. So m1 equals and m2 equals. So we convert we get our roots from this equation. So since we have positive 3, our root number 1 will be negative 3. Then since it is m minus 1, our root is positive 1. Now, rewriting it into our general formula, which is y is equals to c1 e m1x plus c2 e m2x. So, putting all the roots in this equation or in this general formula, our final answer will be y is equals to c1 e negative 3x plus c2e 1x. Now, this is our final answer. Now, we proceed to our number 3 problem. Now, this form or this equation is already written in differential operator form. Then we repeat it with converting it into auxiliary form. So, m2 or m squared plus 2m equals to 0. Now that we have this equation, we will also find the root in this form. So now I can factor out m in our equation. So m equals to m plus 2 equals 0. Since it is already, or it is second degree, we will have two roots. So m1 and m2. So our m1 will be considered 0 and our m2 is negative 2. Then computing it or putting it into our general equation, which is c1 e m1x plus c2 e m2x. So our final answer will be y is equals to c1 e plus c2 e negative 2x.